Good morning. Last time we dealt with numeric data and how to compare two numeric variables. And we talked about normal curve, skewed curve, kurtosis, skewness, and intersection probability. Let me today talk about the binomial variables. The categorical variables, for example, blood group, can have four categories: A, AB, B, and O. But binomial variables will have only two values. For example, sex. The value will be male and female. For example, cause may be present or absent. And for example, effect, it may be good, bad. So there are two values to binomial variables and one value excludes the other. For example, if the result is good, then it cannot be bad. So we'll deal with binomial variables and we will deal with cause-effect association. The cause-effect association in medicine is etiological factor to occurrence of disease, prognostic factor to occurrence of outcome, and type of treatment to occurring of result. Here, the only cause that is in the hand of the researcher is type of treatment or intervention. So such studies are called as experimental studies because it is you who decides what treatment to give. But the etiological factor study and prognostic factor study are God-made and therefore they are called as observational studies. So now we have finished talking about the numeric continuous and numeric discrete data. Now we talk of categorical data. A very special type of categorical data is binomial data. Binomial data is that the variable has only two values, like male or female, and one value excludes the other. For example, if there is male, there will not be female. So let us say here is sex, you can either write male here or you can write female here. All right. So this is binomial data. So let us see how we deal with binomial data. For example, if in the 20 batch, 90 pass out of 100 and 10 fail. So this is fail, this is pass. This is binomial data. You either have to fail or you have to pass. Now in this, there are two ways to express this situation. One is 90 upon 100. Now this is the probability of passing. Okay. But 90 upon 10 is the odds of passing. So there are two ways to express this situation. One is probability and the other is odds. Probability is also sometimes referred to as chance of passing. And if it was an adverse thing like failing, then 10 upon 100 would have been the risk of failing. So it is also referred to as chance or risk. Risk, especially if the event that you are considering is adverse. So after understanding this, let us start to find out the cause-effect association. Cause-effect. Here, in the event of interest, if the event is adverse or favorable, all the time we are seeking the favorable and avoiding the adverse. And we may be doing it at the level of a person, at the level of the doctor, at the level of a community, or at the level of whole mankind. So, all the time we are trying to deal with the events of interest that are occurring around us, the painful and the pleasurable events. So, in medicine, where the usual model is normal to disease to cure to dead, disabled, or lost to follow up. So, dead, disabled, or lost to follow up, which is in between. So, here we don't want this, we don't want this, we don't want this, and we also don't want this. But we certainly want this. So we are trying to accelerate this transition rate and depress these adverse transition rates. So we are trying to depress this, we are trying to depress this, trying to depress this. So this is what basically we are trying to do in healthcare. Now let us understand a little bit about these transition rates. The transition rates, for example, if this is a jar and there is 20 cc of water in it, it is filling at 2 cc per minute and it is emptying at 1 cc per minute. Then after 10 minutes, there will be 20 plus 10, that means 30 cc's of water. Same way, if it is a ward containing 100 people, and there are 20 people here at present. So at present, the prevalence at time 0 is 20 upon 1000. And it is filling at the rate of 2 per day. So this is the admission rate, or it is also called as the incidence rate. Then people are getting cured and discharged at the rate of 1 per day. Then at 10 days, there will be 30 people. We convert it into a formula. Prevalence at time t will be equal to prevalence at time 0 plus t into incidence rate minus attrition rate. Attrition would occur as a rate of death, cure, or loss to follow. In some disease where attrition is 0, like diabetes, in diabetes there is no death, no cure, and usually no loss to follow up. So in diabetes, the attrition rate is 0. Therefore, the formula becomes prevalence at time t will be equal to prevalence at time 0 plus t into incidence rate. Their attrition rate becomes 0. So these are the transition rates. These are the transition rates, the arrows. And we are trying to affect these transition rates by the determinants or the causes of the event. For example, cause can be a etiological factor. Let us say there are lots of mosquitoes, so there will be more malaria. So cause is etiological factor, like mosquitoes. Effect is malaria, and that is disease. The second cause can be a prognostic factor. For example, a person is thin, so his chance of getting cured in a heart attack may be more. So a prognostic factor, and the effect is outcome. And the third thing is that there is a treatment type, treatment or intervention type, and the effect is result. So in medicine, we are basically doing causality research to determine, to find out relation between etiological factor and disease, prognostic factor and outcome, and treatment type and result. So, if the cause and effect are binomial, then say with treatment type A, there were 60 cures out of 100. So 40 did not get cured. So this was cured and this was not cured. And with treatment B, there were, let us say, 30 out of 100 cures. Therefore, the risk or chance, here the event is good, so we'll say the chance of cure with treatment A is 60 upon 100. And the chance of cure with B is 30 upon 100. And if you divide 60 upon 100 by 30 upon 100, you would get a chance ratio or a probability ratio. Or a risk ratio. It can be this also, or it can be relative risk. It can be relative chance, relative probability, or relative risk. Relative chance, relative probability, or relative risk of getting cured given you have treatment A as compared to treatment B. So this is a measure of association between cause and effect. Here the cause is treatment type. Now, there is another measure of association, and that is odds. So the odds given treatment A, odds of getting cured are 60 upon 40. In odds, the denominator 40 does not contain the numerator 60. So this is in treatment A, and in treatment B, the odds is 30 upon 70. And therefore the odds ratio is 60 upon 40 divided by 30 upon 70. If you want to place it like this, it is 60 upon 40 into 70 by 30. So this is odds ratio. So 60 into 70, 60 into 70 divided by 30 into 40. Now this is also called as cross product ratio, because you see that cross there, therefore it is also called as cross product ratio. Then you have done this association in a study population. So here is the universe, whole universe. You have taken a sample of this universe as a study population, and you have determined the measure of association between cause and effect. And that measure of association can be a risk ratio or a odds ratio. Now this, let us say odds ratio is 2. But in the universe, the odds ratio may be 3, maybe 4, maybe 5. So this point estimate, which is the statistic, may not be equal to parameter. Parameter, which is the risk ratio in the universe. Therefore, you convert the point estimate into an interval estimate. You can say 1.5 to 2.5. 1 is in between. 2 is in between. Say you can say 1.5 to 2.5. This becomes the interval. And if you use an interval, it has a greater chance of including the parameter. As the interval gets wider and wider, say let us say 1, 2, 3, the chance goes on increasing that it will include the truth, the parameter in the universe. And therefore there is a measure which not only gives the point estimate as 2, which is the point estimate, but also says a confidence interval. And that confidence interval has a lower value, let us say 1.5, and a higher value, which is 2.5. And the width of the confidence interval, denoted by this number, can be 68%. If it is plus minus 1 standard deviation, it can be 95%. If it is plus minus 2 standard deviation, and it can be 99% if it is plus minus 3 standard deviation. So 3 standard deviation is much wider than 1 standard deviation. So usually the statistics would give you a 95% confidence interval. That means that if you do the study 100 times from the same universe, 95 times you will get a risk ratio between 1.5 to 2.5. So this is what is the association between binomial variables if both cause and effect are binomial. So one way of dealing with categorical variables, one type of categorical variable is binomial when there are only two values and one value excludes the other. So this is about association, cause, effect, association. If both are binomial. Now let us move to say that if the cause is binomial and effect is numeric. For example, you have reduction in blood sugar by treatment A or by treatment B. So let us say that the mean reduction in treatment A, the mean value is 20. Mean reduction in fasting blood sugar by treatment A is 20. And mean reduction here is 50. And of course you will have plus minus standard deviation. So let us say standard deviation here is 3 and standard deviation here is 5. So 68%. The confidence, 68% confidence interval will be plus minus 1 standard deviation. So from 17 to 23. Here it will be 45 minus 5 to 55. 2 standard deviations, 95%. So here 6 will be subtracted from 20. So there will be 14 and 26. And here 10 will be subtracted, so here will be 40. And here it will be 60. So you see that the lower limit of the reduction, 95% confidence interval with B, does not overlap the highest with A. So here is the central tendency, here is the confidence interval, and here you find that the lower limit of the B does not overlap with the upper limit of A. Therefore, this is significant at 95% confidence interval. This difference is significant. And if you convert it into, you are trying to compare mean plus minus standard deviation of A to mean plus minus standard deviation of B, and the p-value that you will get will be less than 0.05. So you can state the significance of difference with a p-value or a confidence interval. So that is the significance. Of course, the magnitude of difference would be the risk the mean reduction in A minus mean reduction with B. So that will be the magnitude and that will be the significance of difference if you are comparing. If the cause is binomial, treatment A and treatment B, and the effect is numeric. That means reduction is 20 plus minus 3 millimeters of mercury with A and 50 plus minus 5 millimeters of mercury with B. So now you have said cause is binomial and effect is binomial. Now we go on to when both cause and effect are numeric. So when both cause and effect are numeric, the cause is on the, let us say, y-axis, cause is on the x-axis. These are the values for the cause. Increasing values from 0 to 10. Alright, for example, it is the dose of drug, and here is the reduction of blood pressure. That means effect. Then you will have a scatter trend. This is called as a scatter plot. And you will find that this dot means that when this was the drug, this was the level of effect. For example, if this was here is a dot, so if this was the magnitude of cause, let us say 10 milligram, and then this was this much is the effect. Let us say 15 millimeters of reduction in diastolic blood pressure. So there is, each dot represents an association between the x-axis and the y-axis. So this is the y-axis and this is the x-axis. Now what you do is that you try to draw a line, which is closest to all the dots. And how do you find it out? For example, this is your estimate. This is your estimated value by the line. And this is the observed value. So there is a difference between the observed and associated value. And this difference is positive. But for this dot, the effect, the estimated value and observed value, the value is negative. So for all the dots, you find out observed minus estimated, and you will get plus values and you will get minus values. So you square them, and as you square them, the sign disappears, and then you add them up. So there is a sigma or addition of observed minus affected square. This is called as residual square. What your trend line, this line which is the line closest to all squares, this is called as the trend line. This is the trend of association between A and B, and this is called as, this value is called as R square. Basically, this line will have the least R square. So it is also called as the least square line. The mathematical value that you get from this of this is that A will be equal to beta 0 plus beta 1 x1, where beta 1 will tell you how much will be the increase in the y-axis as compared to the x-axis. So this is called as linear regression. So we have told you how to associate cause and effect by three methods. When both cause and effect are binomial, by this 2 by 2 table. When cause is binomial but effect is numeric, and when both cause and effect are numeric. So this is the study of causality.